So, does this fit in theoretically? So it turns out, and Einstein didn't appreciate this, I mentioned Chandrasekhar talking about Einstein's understanding of general relativity was very limited. Repulsive gravity is a feature of Einstein's theory. Now, I don't mean that studying general relativity is repulsive. I mean that according to his theory, gravity doesn't always pull things in. It can be repulsive. Only very strange stuff that you'll have to ask me about later has repulsive gravity, and I'll give you one example. And this is the term I coined for it, dark energy. So dark energy, it's an energy-like stuff. It's really weird stuff. I'll give you one example, but it's right there in his equations. So we can understand it. And in fact, this dark energy, the simplest example of dark energy was his cosmological constant. I thought I would just let you in on how we name things in science. So we got a focus group together in May of 1998. And here's what we were test marketing, funny energy. I really liked funny energy. That's really great, because science can be off-putting. It can be a little, scary. And so then I said, oh, that's terrific. And, and how do you feel about, we're going to need to spend about $1 billion to figure out what funny energy is. And they said, well, you need a more serious name. So then my son handed me this Pokemon card, which is now I sort of made a mistake here. So this is the dark energy card, but it turns out it's dark for those of you who can read the kanji, it's dark in the sense of, evilness. But anyway, dark energy, dark matter, it really works nicely. So here's an example. This is the Zen part of my talk. We're getting near the end of the talk, and this is the Zen part. So this is an example of something we know has repulsive gravity. So the question is, what is nothing? Nothing is something. So according to quantum mechanics, the vacuum is filled with particles living on borrowed time and borrowed energy. So this is physics, not politics. This is not a talk about our economy. This is, so according to quantum mechanics, an electron and a positron can pop out of the vacuum, borrow the energy to do so, and then disappear. And this is happening all the time. Willis Lamb at Columbia University, or no, maybe he was at Chicago, I can't remember. Well, he was at O'Hare once. Measured the effect of this, we call these virtual particles, measured the effect of this on hydrogen. So there really is this, the vacuum is seething with these, we call them virtual particles. And if the virtual particles weigh anything, and that's the big question, if they, if you add up how much they weigh, their gravity is repulsive. And so the theorists have tried to add up how much nothing weighs, and we get more or less the right answer. We're within a factor of 10 to the 55. Not bad for a first try. So that's not good. And so what's wonderful about this is now we have two problems. So why does nothing weigh so little? And what's causing the universe to accelerate? So now we've got two problems, which is better than having one problem. Everybody understands that. So this is an example of dark energy, and actually mathematically this is equivalent to Einstein's cosmological constant, which is why he was put on the cover. I think that's all I want to say. So again, view this as a Monet painting. So more observations, it all fits together. The observations not only come from supernovae, but something called baryon acoustic oscillations from the microwave background. And if that weren't good enough for you, they were certified by Sweden. Last October, Brian and Adam Rees and Saul Perlmutter were awarded the Nobel Prize. Actually, they were awarded the Nobel Prize in December. It was announced in October. Okay. Oh! In science, expert testimony is very important. And so, again, not everyone's a scientist, so I carefully watched this whole interview. And towards the end, Katie Couric asked Sarah Palin, about dark energy, and she said, "You betcha, Katie, I believe in dark energy. We can see it from Alaska." So there you go. That's even better than, that was before the Swedes. And so once she learned about dark energy, she wants to drill for it. Okay. So I've largely been telling you this, and I want to wind down now with just a couple more with the big punchline here. But so I told you about the go-go junk bond days in the 80s, and it looked like we might just rise ever upward in our own hot air. I think I said that last time. But we started getting data, and probably the most important data was measurements of the microwave background. Remember, the microwave background gave us a record of the universe at a very simple time, and the first inkling that we got of this was from a satellite launched by NASA called the COBE satellite. And I mention it because one of the people on the COBE team's father is actually in the front row. And it showed us that the microwave background was very smooth. It showed us that there was a big hot spot and a cold spot because we're actually moving, and so in the direction we're moving it looks hotter. And then it gave us the face of God. That's what George Smoot called it. George Smoot later got the Nobel Prize. And this is the first inkling we had of those small fluctuations. And so that kind of started us on a really good path to where we are today. So that's why I showed that. Here we are. This is the picture of the lumpiness. 0.001 fluctuation. Sorry, 0.001%. How big is that? That was the difference in the vote count between George Bush and Al Gore in Florida. And this is also a map of the very, very young universe. Where it's red, there was more matter. Where it's blue, there was less matter. There's Stephen Hawking. And so how do we learn from this? We stare very hard at it. Actually, that's not quite true. What we actually do is do a mathematical operation that I'm not really going to tell you about because it's not important. But if instead of looking at the map this way, we actually make a plot of the difference in temperature or intensity between 2 points separated by different angles on the sky, this pops out. And I show you the WMAP data in red, and then the results of my colleague at Chicago using the South Pole Telescope in blue. And I also show you this black curve, which is what's predicted by inflation plus cold dark matter. Ooh, good, I like those oohs and ahs. That must have been the smart people. I'm still listening for the, I can't say the word tolerant. And what else did I want to say? So what's amazing about this is the reason that there are these bumps and wiggles is that in the universe, the dark matter is trying to form structure. The atoms want to fall in and join in, but the photons push them out, and so the universe is ringing like a bell. And Mark can explain this better than I can. And so the various bumps and wiggles here tell us what the universe is made out of. So by analyzing the sounds made by the universe, by this ringing, we can learn a lot about the universe. And so this is what we've learned. So where this big guy is, where it is on this axis, tells us the shape of the universe. And it tells us that we have the flat universe. Of course, we already know it's accelerating. And I talked about the journey from quark soup to nuclei and atoms and galaxies. And then the microwave background fills in a lot of the numbers. That the atoms are 4.6 plus or minus 0.16% of the total. And the exotic dark matter is 22.7 plus or minus 1.4. You add these two together, you get a number close to 28. 73% dark energy. If you add in the information from the microwave background, you get a Hubble constant that doesn't have this extra error bar. You get an age, oops, I screwed up on the age. You get an age of the universe of 13.75. I screwed up because I forgot to, I showed this slide a week ago and I didn't add the extra week. We're not that good yet, but we have an age of the universe, 13.75, And all of this is consistent with inflation. That theory curve passes through all the data points. And, oh, I want to tell just a little bit of story here. So the astronomers, bless their heart, and you're from the South, so you know what that means. Once I say bless their heart, you have to add one about it. When we first told them about inflation, we said, you get a flat universe, i.e. that these numbers add up to 100%. And they said, oh gosh, we really love that story about false vacuum energy and the Jiffy and all that. But you know, the universe, the density is 10% of the critical density. And well, we said, you know, but there's a lot of dark matter around, and you haven't accounted for the dark matter very well. And so the dark matter brought the total up to, if you add those two numbers together, you get about 27.3. And so the astronomers thought, you know, we got them. It's not 100%. They're not going to get to the critical density. And then in 1998, the universe turned out to be speeding up, and this other component was identified, the dark energy. And it's such a wonderful story. At the very last minute, we come in with the, you know, 73% necessary to make the universe flat. Remember, a flat universe has a critical density, which I think this slide shows. So we had these three possibilities. You were all getting nervous because you're going to have to learn non-Euclidean geometry. You don't. We're the uncurved universe. That's us. Okay. So I just thought I would remind you of some things about the universe. It's very, very pretty. But the dark side is where the action is. Stars are 0.5%. The hot atoms are about 4%. The dark matter, this exotic dark matter, is about 24%. The dark energy is 71%. I can see the numbers are a little bit off, but 70%. So, you know, the stars are only 0.5% of the universe. The stuff we're made out of isn't even 5%. That's an amazing